Hello everyone. I'm back. Computer issues are hopefully fixed, and this is going to be my video on the HR diagram. It should be a short video, but we will see. So for the HR diagram, you should have two um, items open. You should have the star table here. This is the absolute magnitude star table, which is the big M, and the little m is the apparent magnitude, which you should not use for most of this, but there may be a few things that you might use it on. Let me open the actual lab itself. So the lab is right here, so I have that. Oops, it's right here. There are not a ton of questions on here, but there are three graphs that you need to know. The questions you will want to answer, I guess, afterwards. I guess the lab could be reworked to show that, but it says we will generate a main sequence curve, and you're going to plot all the stars on table 3 into figure 1 and sketch a smooth curve through them. So basically just draw a smooth line. Don't necessarily connect the dots, but just draw a smooth curved line through them. All these stars are luminosity class 5 dwarfs, so they are not super giants or anything like that. Let's see. So plot the stars in table 3. So table 3, let's pick up table 3 here. These are table 3 main sequence stars. There's not that many. There's the Sun, Gamma Ceti, Alpha Hydrus, Kruger 60b. These are just different stars. You can see they are all absolute magnitude. Now, the number one thing here is that you pay attention to the plus and negative signs, even though most of these are positive. So if we go back, sorry, I'm terrible at this. If we go back, you're going to want to plot these on figure 1. So we have B0 all the way to A, F, G, K, and M. So the traditional like moniker is "Oh, be a fine girl, kiss me." And I know that sounds silly, but it is literally what every astronomy student ever has ever learned. There would be an O here, O, B, A, F, G, K, M, but there's not an O on this chart, so that's fine. So B0, and then you have B2, B4, B6, B8, and then A0. So if you have a 1, 3, 5, 7, or 9, they're going to be in between these little hash marks here. And your magnitude sign is going from positive to negative, because negative, remember, means that it's brighter. So if you have a I don't know, a B1 star that's -7, you're going to go here and you will go up 5, -6, -7. Okay, a lot of people intuitively, and it's fine, want to count down -5, -6, -7. Don't do that. The negatives go higher as you go up. So just remember that this vertical scale, the negatives are on the vertical, which go up as you get brighter and brighter and brighter. It's a weird system. I'm not saying it's a good system, but it's a weird system, and that's why that happens. Okay. So For this lab, you're going to plot all of these stars, the stars that it says on here, and on here. You're probably gonna have to print it out, unless you have some kind of weird, crazy, fancy way of manipulating documents and stuff. I mean, if you do, that's fine. I'll take it, but if you don't, I would print it out and plot it myself. Okay. So, the procedure here, you're going to generate a main sequence curve. Now, add the stars of table 4 to the plot you just made and circle them. So table 4 is going to be these stars. These are 4 stars. And you can see that these are not dwarf stars because they don't have a 5 or a Roman numeral V around them. These are giant stars. Okay. So you're going to add Arcturus, Capella, Alderon, and Pollux to that curve. And I will get to these questions here in a minute. But let's go down here. In figure 2, plot all the stars from table 6. Big M, so it's the absolute magnitude on the vertical scale. Note that table 6 is a list of all the brightest stars in the sky, not necessarily the closest, but they're just the brightest. And you're going to transfer the main sequence curve from figure 1 onto figure 2. So all I want you to do right here is draw that smooth curve that you made onto the next graph. So the curve that you drew here, which should go down something like this, you're going to draw on here. It doesn't have to be perfect. It's fine. It's fine if it's not perfect. Don't worry about it. But just somewhat of a semblance of that smooth curve that you did in the first graph. Now, you're going to answer these questions. What is the most common type of bright star? And you're going to estimate the absolute magnitude of these stars. So, how to do that is you're going to have a lot of stars over here. You're going to have a bunch of stars over here, and I can't show you, but I can, kind of estimate, because I know there's going to be a bunch of dots over here. Now, to estimate, all you have to do is kind of draw a mental line, or if you have a ruler or something, it's fine. You can put that in the middle of the top and bottom stars, and then draw a line over, and wherever it hits over here on the vertical axis, that's your estimate. Okay. So you do not have to add them all up and divide by the number of stars or anything like that. I mean, you can do that, but that would be silly. You're just wasting your own time if you do that. You're going to have a bunch of stars, a bunch of dots over here, basically up here in this top region. All you need to do is put a sheet of paper or like I said, a ruler or something like that, and estimate in the middle. So you need to have as many stars above the ruler or sheet of paper as you have below it, and you'll estimate over here. It's not too hard. It doesn't have to be super exact. That's why we say estimate, and that's fine. So you'll do that. You'll answer these questions. You can just circle for 5 and 7. That's fine. And then 8 and 9 is basically the same thing, except you are doing table 7, which is the nearest stars. So table 6 was the brightest stars. Table 7 is the nearest stars. And with that, you're going to estimate once again. I would not worry about this. I mean, you can. Never mind. You'll notice that the apparent magnitude is negative 26.8. The absolute magnitude is a 5, which means that it's barely visible to the naked eye. So, with this, plot all of them on here and answer the questions on table 3. Same stuff as before, not too bad. Let's go back to the first part. So for the first part, you will answer these questions. Why don't these stars on table 4 lie on the main sequence? I kind of already told you that. Main sequence stars have dwarf stars, but table 4, we have giant stars. And giant stars, excuse me, they don't lie on the main sequence because they're giant stars. They are not fusing hydrogen anymore in their cores. They are fusing helium. So I basically just gave you the answer. So let's pull up something that will help you with the how many times brighter is Capella, ratio of brightness, etc. And here we have it. Okay. So we have the magnitude scale, the ratio of brightness, basically. So with this magnitude scale, and we've talked about this, we should have talked about this before, or you should have read about this. Excuse me. Magnitude scale is based on a 1 to 6 scale, where 1 are the quote-unquote brightest stars in the sky, and 6 are the dimmest stars in the sky. And this is taken off of a PDF, so it's kind of wonky here. But every magnitude difference is 2.512. So a magnitude 1 star is basically 2.5 times brighter than a magnitude 2 star. And a magnitude 2 star is basically 2.5 times brighter than a magnitude 3 star. In this compound, so it doesn't multiply, or I mean, excuse me, it doesn't add, it multiplies. So a magnitude 2 star compared to a magnitude 5 star, that's 1, 2, 3 times. If you put 2.512 raised to the third power, so it's 2.512 times 2.512 times 2.512, is actually about 16 times brighter. So if you have a star that is 3 magnitudes brighter, it's about 16 times brighter. Okay? So if you do that with 5 magnitudes, let's say from a 1 to a 6, that's about 100 times brighter. So 2.512 raised to the 5th power, or if you multiply it by itself 5 times, that's about 100 times brighter. And spoiler alert, just to get you on your way, that's what Capella is going to be compared to the sun. Absolute magnitude is whenever you, and you should already know this, hopefully, you measure everything relative to a singular distance, so you do not have distance to take into account. So if we were to move the sun, which is an apparent magnitude of 26.5, back down to 10 parsecs, which is the standard distance that we measure everything, it would become a 5.0 magnitude star, which means that it's barely visible to the eyes. 1.3 would go down to, let's say, a 6.0. A 4.2, we're going to move it up, and that's going to go to a 0 magnitude star, which is fairly bright. 3.3 up to a 2.0. And then if you had a star at 10 parsecs, there is no star at 10 parsecs, but let's just say if you did, it would be a 2.0. Okay. Sun spectral luminosity class is a G2V star, which is on the main sequence because our sun is not a giant yet. It will be in about 5 billion years, but the main sequence is here. Most of the stars are on here. And our sun is here. So the luminosity class, we have supergiants, which are 1A and 1B. We have bright giants, which are 2 here. We have giants, which are 3, Roman numeral 3. Then we have subgiants, which are 4. They have just left the main sequence. And then we have dwarfs, which are on the main sequence, which are most of the stars that are burning hydrogen right now. And you can see here, like Betelgeuse, which is in Orion, is a giant star. It's a supergiant star. It's about 300 times the radius of our sun. And our sun will become a giant at some point. You can see the astronomical unit. It may not become a supergiant, but it will become a giant star at some point. This is where the Earth resides, basically, as it orbits around the sun. So you can see Betelgeuse almost gets out to Mars's orbit, which is pretty crazy. These supergiant stars do pulse in and out. They do get smaller and larger, not by a very great amount, but they do. So this here is just to show you a couple of sampling of different stars and how big they get. So, stellar luminosity, total amount of radiative energy emitted each second. It depends on the surface area. So how bright the star is, the luminosity is like the intrinsic brightness. Like if you have a light bulb and it says like 100 watts, that is the luminosity of that light bulb. So we have surface area, which is the size of the star. So how much that star emits from the area of the surface of a sphere. We're modeling these stars as spheres. And then we have the temperature. How hot is the star? Okay. So, ooh, I skipped a lot of these things. So here we have stellar brightness. This may be something that you may want to pause or whatever, but this is a table showing you the ratio of the difference in magnitudes. Now, the difference in magnitudes are here. It does not matter what magnitude it is just the difference in magnitudes. Okay, so if you have a difference of 2 or 3, you want to use the scale. It's 2.512 raised to the difference of those magnitudes. So if you have a difference of 1, it's about 2.5, 2.5. We're just rounding here. If you have a difference of 2, let's say a magnitude 3 compared to a magnitude 1 star. Okay, that's a difference of 2. You know, 1, 2, 3, that's a difference of 2. This is a difference of 6.3 in the brightness. Okay, so this is the flux here. If you have a difference of 3, it's about 15.9, 16, let's say. If you have a difference of 4, it's 40. If you have a difference of 5, it's 100. Hint, hint, hint for the lab. And if you have a difference of 6, let's say you're measuring a magnitude 0 star compared to a magnitude 6 star, it's going to be 251 times brighter or dimmer, depending on which star you're looking at. You know, if you're comparing the magnitude 6 star to the magnitude 0 star, it's going to be 251 times dimmer than the magnitude 0 star, let's say. Okay, so you have your HR diagram. It should look something like this when you plot it. It's fine. Let's say you have a G2 star like the sun. It's a +5. You'll put it there, and then you'll plot all the other stars there. And here is another main sequence line down here. It's not too bad. Okay, so here is a sample problem. It's not too difficult. We have the same radii of stars, but one is twice as hot as the other. So we want to know, like, what is the luminosity? What is the energy radiated from these stars? So our Stefan-Boltzmann law is over here. E, the energy equals sigma times T to the fourth. Okay. So whenever you're comparing things, you want to divide them. So let's say we have E1, our first star, over equals sigma. Sigma is just a constant. You don't even really need to know what it is because it's going to divide out if you divide these things. It is just a constant. It's not to be worried about. And then you have the temperature of the star. So let's say that you have these two stars here. You have the sun, and let's just say copy paste. Let's just say you have two of these Stefan-Boltzmann laws, and you're going to divide them. Imagine there's like a division sign between here. So you have the energy of one equals sigma times the temperature of one star to the fourth. And then you have the energy of the second star equals sigma, which is always the same, times the temperature of the second star to the fourth power. Okay. So we have, let's say this is E. Oh, I don't know how I want to do this. Let's say this is E2, this hot star here. Let's call this hot star E2. And then, oops. There we go. Call this star E1. Okay, let's call this E2. Let's call this E1. Let's call this T2. Let's call this T1. Okay, the same size though. And we're dividing them. So this sigma divides out. It doesn't matter. Sigma divided by sigma is 1. It doesn't matter. Anything times 1 is itself. So, E2. We need the temperature of this star. It's 12,000 degrees Kelvin. Okay. And this one's 6,000. So T1 is 6,000. T2 is 12,000. 12,000 divided by 6,000 is what? It's 2, right? 12,000 is twice as hot as 6,000. So you have 2, and to the fourth power, if you were to divide these, the fourth power would go on the outside of the bracket. So T2 divided by T1 to the fourth power. Okay. So all we have here is 2 to the fourth. And if you were to do that in your calculator, it's actually 16. 2 times 2 times 2 times 2 is 16. So the total output, or the total luminosity, the total energy radiated by the star, is 16 times the energy of star 1. Okay, hopefully he followed that. Hopefully I explained it as well as I could. Okay, here's something a little bit different. And this is what you're going to have to do in your lab. Okay. So, similar idea, but slightly different. You need to know the radii of the star if it's brighter. Okay, so these stars are the same temperature, however, their radius is different. And this is going to be what's going to happen between the sun and Capella in your lab. Okay, because that's what your lab is asking for. If we go back to the lab, if I can find it, lab worksheet. How many times brighter is Capella than the sun? So I'm going to walk you through it. You're going to have to figure out how many times brighter Capella is than your sun. And to do that, you're going to have to measure their magnitude. So you're going to have to go over to your HR diagram, excuse me, your tables, and look, the sun is a 5 and Capella is a 0. So how many times brighter is that? Well, 5 minus 0 is what? It's 5. And you're going to have to go to that brightness scale that I showed you earlier and figure that out. That's that 2.512 raised to the difference in magnitudes. Okay. But let's do this one. You need to do the Capella one on your own. So star 2 is more luminous than star 1 by 3 magnitudes. This is a magnitude 2 star, magnitude 1 star. Star 1 is a 5. 5 minus 2 is 3. If we go to this magnitude ratio here, it's about 15.9 or 16. Let's call it 16. Star 2 is 16 times brighter. Why is that? Well, it's because it has 16 times the surface area. So, for instance, whenever you go to your lab, it says, how many times brighter is Capella than the sun? Well, it's going to be X amount times brighter. How does the surface area of Capella relate to the sun? Well, it relates because it has that much surface area compared to the sun. However many times brighter it is, whatever number you get, hint, hint, it should be a fairly whole round number. It's going to have that much surface area compared to it. And I really wish we were in class because I could kind of show you better. But these two numbers, 2 and 3, are the same number. It's that much brighter because it has that much surface area. So if it's emitting the same amount of energy per area, it has that much more surface area compared to the sun. Okay, number 4 is the biggest one. It's going to be the one that's going to get most people, which is how does the radius of Capella compare to the sun? We're not going to do Capella. We're going to do this example here. And this is the surface area. So this one, since it's 3 magnitudes bigger, it has about 16 times the surface area. Okay. So, surface area of a star. It's 4 pi r squared. Okay. So the luminosity equals the surface area of this star. Okay. So what they're doing here is they're equating luminosity with surface area, which is fine, because they're both the same temperature. So it's actually the surface area times Stefan Boltzmann law, which we went over here. Sigma times temperature, but those cancel out because they're the same temperature here. So what we're essentially left with, if we have the same temperature star, but they're both bigger or smaller, it's 4 pi times the radius of that star squared. Okay, the 4 pi's cancel out. So we're basically left with 16 over 1 because we're comparing it to a star. So Since this is 16 times brighter, because it's 3 magnitudes, 16 times as bright as the original star. So 16 over 1. So basically 16, right? We go over here. Surface area compared to the other surface area, 4 pi r squared divided by 4 pi r squared, r2 squared, r1 squared. The 4 pi's cancel out. 4 pi divided by 4 pi is 1. So that is why we're left basically with this equation on the right-hand side, which is the radius of the second star squared divided by the radius of the first star squared equals 16 over 1. Because it's 16 times brighter, because of this magnitude, than this star. Okay, so we don't need the radius squared, though. We just need the radius of the star. So if we take the square root of both sides, this is r2 over r1 squared. Take the square root of that. 16 divided by 1. Take the square root of that. So this becomes r2 over r1. So we got rid of the squared. It becomes 4 divided by 1. And if we were to cross multiply everything, we would get the radius of star 2 is simply 4 times the radius of star 1. Now, I'm going to give you a little hint. Capella is going to be 5 magnitudes greater, which it's going to be 100 times the flux. Okay, I've basically answered 2 questions for you. So instead of 16 here, it's going to be 100. Okay, so what happens when you take the square root of 100? And that is all I'm going to say. I've basically done the entire lab for you. Hopefully that was semi-intelligible. I hate this working from home. I really do, but that's all we have. So I hope that helped a little bit anyway. Okay, I will see you guys later. Have a great Thanksgiving break and take it easy.